So let us start the lecture. In the previous lecture we have seen that spatial post-semigroup amalgam is weakly embeddable. Today we will derive a relationship between between a spatial post-semigroup amalgam and dominion, because it's very difficult to check whether a given element belongs to dominion or not, because you have to check those that definition. If you see the definition, so from definition you will see that you have to check for all morphisms beta and gamma which agree on U, then they should agree on D. Okay, so it's very difficult to check whether given element belongs to the dominion or not. So in order to overcome this problem, Isbell have given the following theorem. It's not the Isbell-Zizek theorem. So after this we will discuss that theorem. But this theorem is also given by Isbell, and it's a relationship between the semigroup dominion and spatial post-semigroup amalgam, and the theorem is following. So this is our theorem. Let S be a monoid and U be a submonoid of S. Let S be a monoid and U be a submonoid of S. Let S be a monoid and U be a submonoid of S. Let S dash be a monoid disjoint from S, or you can say S prime. Let S prime be a monoid which is disjoint from S. And let alpha be an isomorphism from S and S prime. From S to S prime be an isomorphism, be an isomorphism okay. So let this be it is a free product of that amalgam S star S or U. It's S prime, sorry, be the free product of the amalgam of the amalgam A equal to, sorry, it's in square bracket U, that's the core of this amalgam, and this is it's a set of two semigroups, and we have the set of two morphisms. One is the inclusion map and second is alpha restricted U, where I from U to S is the inclusion map. Of U onto S. That's, and let that mu and mu prime, तो जो हमने प्रीवियस थ्योरम में देखी ना, म्यू एंड म्यू प्राइम, these are those mappings actually. Mu and mu prime be the natural maps from S prime respectively into P. the free product of this amalgam, okay, which is also the push out of that diagram, okay. So then we have the following relationship: image of S under mu intersection image of S prime under mu prime, okay, the inverse image of this intersection under this mu inverse, okay, it's equal to the dominion of U in S. तो अगर आपको चेक करना होगा कोई एलिमेंट डोमिनियन में है, आपको ये चेक करना है कि वो एलिमेंट इसमें है, एस म्यू इंटरसेक्शन एस प्राइम म्यू प्राइम ऑफ म्यू इनवर्स। तो अब आपको वो मॉर्फिज्म नहीं फॉर ऑल बीटा गामा मॉर्फिज्म्स व्हिच एग्री ऑन यू, कि वो आपको नहीं लेना है, अब डायरेक्ट आपको ये चेक करना है। So and this theorem is given by Isbell, okay, it's given by Isbell, but it's not Isbell's theorem because Isbell's theorem is different, okay, it is given by Isbell, but that famous theorem which that's a different actually, that's a very important theorem, और यूजुअली वही थ्योरम उसी थ्योरम की इम्पोर्टेंस से वही यूज की रिसर्च में भी हो रही है, दैट्स वेरी इंपॉर्टेंट थ्योरम, दैट थ्योरम इज कॉल्ड द Isbell's zigzag theorem. So let's try to prove this theorem first. Proof. Okay, so we have the following commutative diagrams that we have seen in the previous theorem for the special post-semigroup amalgam. We have the following commutative diagrams. Now the first one is this U to S, it's the inclusion map, then U to S prime, it's alpha, in fact it's alpha restricted U actually, then we have P here, and S to P is mu, S prime to P is mu prime. So this is one of the commutative diagram, so name it say 1, okay, diagram 1. And the second commutative diagram is first U to S, obviously it's the inclusion map here, so I think we don't need this thing, okay, we need the following diagram actually, so that's this diagram जो आपने previous theorem में वो diagram में लिखा था, it's P first here, it's push out diagram actually, mu mu prime, here it's S prime, here it's S, okay, it's S here, yeah, and this is the identity map from S prime to S prime, and from S to S prime it's alpha, and this delta exists, it's from previous theorem actually, delta exists from P to S prime, so it follows from the push out property of P, okay, this is delta, that this we have discussed in the previous lecture. So we have these two diagrams, okay, diagram 2, so from diagram 1, from diagram 1 the monomorphisms the monomorphisms mu from S to P and alpha mu prime. It's a composition of alpha is from S to S prime and mu prime is from S prime to P. So it is from S. It is also from S to P. S to P. Have the following from the diagram 1. These two monomorphisms have the following properties. These two mappings, actually you will see that these two mappings, they are morphisms, and you will see that they agree on U. They agree from this diagram 1. Okay, they agree on U. So we check U mu. We will show that U mu is equal to U alpha mu prime. U mu is equal to, अब डायग्राम से इसको देखिए ये किसके बराबर है, U mu. So it's this U mu is equal to I U mu. Okay, it's equal to U I mu because I of U is U. But from this diagram, this I mu is equal to, from diagram 1, it's equal to alpha composition mu prime. So it's equal to U alpha mu prime by diagram 1. So U mu is equal to U alpha mu prime. Okay, this is true for each U nu. Okay. For all U belongs to U. Now we come to the proof of the theorem. So let's assume that first D is in the domain. We will show that D is in that intersection. Let D belongs to dominion of U in S. By definition, इसका जो आपने यहाँ पर इसका नाम आप स्टार रख दीजिए. By definition, for any two morphisms, obviously they are monoid morphisms, beta gamma from S to T, where T is any semigroup, T is any monoid, for any two morphisms, semigroup morphisms, we have this U beta equal to U gamma for all U in U implies D beta is equals to D gamma. Okay, so this is true whenever we have morphisms beta gamma from the semigroup S to any semigroup T such that U beta is equal to U gamma. This should imply T beta is equal to D gamma. But here you will see that this mu and alpha mu prime, so these are the morphisms from the semigroup S to P, from the semigroup S to P, such that these two morphisms agree on U. Okay, these two morphisms agree on U. तो यहाँ पर क्या है आपके पास, देखिए डोमिनेंट की डेफिनेशन क्या है. अगर कोई भी दो morphisms आप लो from the monad S to any monad T, कोई भी monad आप लीजिए और कोई भी दो morphisms दीजिए जो U पर एग्री करे, then they must agree on T. अगर D डोमिनेंट में होगा, अगर D डोमिनेंट में होगा, तो यहाँ पर क्या आपके पास मॉर्फिज्म्स है, म्यू आपके पास मॉर्फिज्म है और अल्फा म्यू प्राइम आपके पास मॉर्फिज्म है. और इन दो मॉर्फिज्म्स की प्रॉपर्टी क्या है, दे आर द मॉर्फिज्म्स फ्रॉम S टू P. तो जो T सेमी ग्रुप है इसको आप रिप्लेस कीजिए P से, बिकॉज T इज एनी सेमी ग्रुप, T इज एनी मोनाइड. इसको आप किसी भी मोनाइड से रिप्लेस कर सकते हैं. इन पर्टिकुलर यू कैन रिप्लेस इट विद P. और बीटा गामा कोई भी मॉर्फिज्म्स है आप इनको रिप्लेस कर सकते हो म्यू और अल्फा म्यू प्राइम से, बिकॉज दे आर आल्सो द मॉर्फिज्म्स on S. They are morphisms from S to P. So by star, we must have d mu is equal to d alpha mu prime by replacing, or you can say by putting, okay, by putting what? Beta is equal to mu, gamma is equal to alpha mu prime, and this t, it's equal to p. So d mu is equal to d alpha mu. So d mu means d mu, it belongs to what? D is in dominant, or D is in S, okay? So d mu belongs to S mu, and this d alpha mu prime, this belongs to what's this d alpha? It belongs to okay, d alpha है आपका, जो मैं अब d alpha को मैं अलग से लिखूंगा, d alpha of mu prime. What's alpha? Alpha is a map from S to S prime. So d alpha belongs to S prime. So this element belongs to S prime mu prime. So it's a d mu, okay? So d mu belongs to S mu, and d alpha mu prime belongs to S prime mu prime. But d mu and d alpha mu prime, they are actually same elements, they are equal. So this gives d mu, it belongs to the intersection S mu intersection S prime mu prime, which means that d belongs, you can apply mu inverse on both sides, it belongs to S mu intersection S prime mu inverse. तो d आपने डोमिनेंट से लिया था, d इसमें आ गया, therefore डोमिनेंट इज सबसेट ऑफ, therefore dominion of U in S is subset of S mu intersection S prime mu inverse. So now let's take an element in that intersection. Now let's take D belongs to S mu intersection S prime mu inverse. So it means that d mu belongs to this intersection. So that means we can find an element S prime in S prime. So that means that d mu, it belongs to S mu intersection S prime mu prime. So d mu belongs to S prime mu prime. Let's use this one. So there exists S prime in S prime such that d mu is equal to S prime mu prime. Now from diagram 2, we have, let's see the diagram 2. We have S prime. What's S prime? S prime is equal to S prime is equal to, let's see the diagram 2 first. Diagram 2, okay, this is diagram 2. S prime is one S prime. You can see from this diagram these two compositions, okay, composition of mu prime and delta is equal to the identity map. So S prime means the image of S prime under 1, but 1 is equal to mu prime delta. You can see from this, because the composition of mu prime and delta is the identity map. So from diagram 1 you can see that from diagram 1 we have S prime, it's equal to S prime of 1, that's equal to S prime, this 1 is equal to this one is equal to, from that diagram you can see that this one is equal to mu prime delta, okay, because 1 is equal to mu prime delta. Okay, and this s prime, it's equal to s prime mu prime of delta, but this s prime mu prime, it's equal to d mu, it's equal to d mu, okay, it's equal to d mu of delta. But this mu delta, again from that diagram, mu delta, let's see that what's mu delta from that diagram. Mu delta, it's equal to alpha, I think. Mu delta, the composition of mu and delta. So let's see that diagram first. Diagram 2, okay. What's the composition of mu? It's mu, it goes in this direction, mu and delta, okay, it goes like this. The composition of mu and delta is equal to alpha, so mu delta is equal to alpha, mu delta is equal to alpha, mu delta is equal to alpha, this is equal to d alpha, because mu delta is equal to alpha. ओके तो आपको ये मिला है, दिस s प्राइम इज इक्वल टू डी अल्फा। आपने d लिया है इंटरसेक्शन से, ओके, आपको प्रूव करना है d इज इन डोमिनेंट। सो तो डोमिनेंट क्या, वी शो दैट d बिलोंग्स टू डोमिनियन ऑफ u इन s। तो इसको प्रूव करने के लिए आपको क्या करना है, कोई भी मोनाइड आपको लेना है, लेट d बी एनी मोनाइड, and beta gamma b morphisms, and beta gamma b morphisms from S to T b morphisms. So obviously monoid morphisms, okay, because we are in monoids here. Such that u beta is equal to u gamma for all u in u। आपको प्रूव करना है d बीटा इज इक्वल टू d gamma, ओके, क्योंकि आपको प्रूव करना है d डोमिनेंट में, राइट। So we have a following commutative diagram. You can see that diagram here. We have, so let's first verify the commutativity of the diagram, then we write the diagram, okay. So we have the following, we have u, we have u of I beta is equal to u beta, that's equal to u gamma, and that's same as u, let's write here this alpha restricted u, then alpha inverse and gamma, because alpha inverse is the identity map. So for all u, so therefore we have the following commutative diagram. We have the following commutative diagram. This one, u to s, then s to t, okay, it's here u to s prime, then s prime to t. U to s is the inclusion map, s to t is the beta, okay, and u to s prime is the alpha restricted u, and s prime to t you take this map alpha inverse gamma। आपको alpha restricted u इसका composition alpha inverse gamma के साथ, alpha inverse gamma। So we have this commutative diagram, टी के लिए आपको कम्यूटेटिव डायग्राम मिल गया. बट सिंस P is a push out of the same diagram, so there is delta. Since P is the push out of the same diagram of the same means the above diagram. Okay. Therefore, there exists delta from where to where, from P to T. Let's write this as zeta, not delta. Okay, let's write this as zeta. So zeta is the morphism. Okay. From P to T, such that जो आपने कल की थ्योरम जो आपने अभी वो डायग्राम लिखी थी ना, पहली दो डायग्राम, फर्स्ट सेकंड डायग्राम, इसी टाइप की डायग्राम है, उसी टाइप की डायग्राम. वहां पर डेल्टा है, यहाँ पर जेटा हमने लिया S prime to P. Okay, and this is your S to P. S prime to P is mu prime and S to P is mu. Then S prime to T. Okay, we have T here. It's alpha inverse gamma. तो जो आपने अभी लिखा वो मैप alpha inverse gamma, and here it's beta. And this zeta exists from P to T. So therefore there is a zeta such that the diagram right here, such that the diagram this commutes. So this diagram commutes. So hence from this diagram we obtain the following. आपको प्रूव करना d beta is equal to d gamma. So let's start with d beta. D beta. So this d beta, but beta is equal to mu composition zeta. This is d mu zeta, and that's equal to, what's this d जो हमने अभी लिखा है, अभी अगर आप कोई जहन में होगा जो हमने अभी वो रिलेशन निकाली ना, while this one s dash is equal to d alpha. Okay, s dash. So it's d is equal to s dash mu prime. जो पहली इससे पहले जो आपने लिखा ना d, जो इंटरसेक्शन में आपने लिया था d एक्चुअली, तो वहां से s prime exit हो गया, such that d mu is equal to s prime mu prime. Okay, let's use this. Let's write this as say, let's write this as double star. So from this double star, okay, d mu is equal to s prime mu prime. Okay, d mu is equal to s prime mu prime. D mu, okay, is equal to s prime mu prime, and then there is zeta. But this mu prime zeta, what's this? You can see this diagram, okay, mu prime zeta is equal to alpha inverse gamma. This is equal to s prime mu prime zeta is equal to alpha inverse gamma. Okay, here it's mu prime zeta. Okay, mu prime zeta, but this mu prime this s prime, it's equal to s prime किसके बराबर है? Again you can apply the definition of s prime. S prime is equal to d, it's equal to sorry, let's see it again, here. Let's erase this first. Okay, so we have s prime mu prime zeta. Okay, s prime mu prime zeta, and this s prime is equal to d alpha. S prime is equal to d alpha. d alpha. So why it's s prime is equal to d alpha, और यहाँ पर आपने यूज़ किया डी बीटा, डी को आपने लिखा, बीटा को आपने लिखा म्यू जीटा, ओके, ये तो आपने इसी डायग्राम से लिखा, और फिर आपने डी म्यू को लिखा है एस प्राइम म्यू प्राइम, इट्स बाय डबल स्टार, ओके, इट्स बाय डबल स्टार, और अब आपने एस प्राइम को लिखा डी अल्फा, एस प्राइम को आपने लिखा डी अल्फा, सो एस प्राइम इज इक्वल टू डी अल्फा, एस प्राइम इज इक्वल टू डी अल्फा. What is S prime? S prime is equal to d alpha. Let's look at this. S prime. Look at this. S prime is equal to, इसका नाम आप ट्रिपल स्टार रख दीजिए. S prime is equal to d alpha. Okay. S prime is equal to d alpha. So S prime is d alpha. Then we have here mu prime and zeta. It's by triple star. now look at this diagram. Mu prime zeta, okay, mu prime zeta is equal to alpha inverse gamma, so this is equal to d alpha, and mu prime zeta is equal to alpha inverse gamma, and alpha inverse is the identity, this is equal to d gamma, so d beta is equal to d gamma, d beta is equal to d gamma. So thus, तो बीटा डोमिनेट हो रहा है यूज है, डी बीटा इज इक्वल टू डी गामा, सो देयरफॉर डी बिलोंग्स टू द डोमिनियन ऑफ एस. So this S mu intersection S prime mu prime, let's apply mu inverse on this. आपने D इससे लिया था, वो डोमिनियन में आ गया, this is substrate डोमिनियन. So hence equality holds. Hence S mu intersection S prime mu prime of mu inverse is equal to the dominion of U in S. So this completes the proof of this theorem. Now next theorem, which is very important, which actually is well as zigzag theorem. It's not exact, it's not the exact zigzag equations, but from that theorem we can obtain the zigzag equations. And this proof of Isbell zigzag theorem is given by Steenstrom in 1971. Isbell ने जो इसका प्रूफ दिया था Isbell zigzag theorem का, that was in 1966. और उसके बाद जो इसका प्रूफ दिया था, नेक्स्ट प्रूफ जो इसका दिया था, which was due to Steenstrom. And that was given by in 1971. Okay, so that's the next theorem. So we cannot complete the proof of this theorem, but at least we can prove its half part. The next theorem is the characterization of, the next theorem is given by Isbell. The next theorem, let's write this first. The next theorem is given by Isbell itself, but here the proof is due to Isbell in 1966. But we present the proof. We present the proof due to this Steenstrom. In 1971. Okay, so let us state the theorem first. The theorem is that U be a submonoid of monoid S. Let U be a submonoid of a monoid S. Okay, then, and D belongs to S, and D is an element in S. Then this D is in dominion. D belongs to dominion of U in S if and only if D tensor 1 जो आपने डिफाइन किया equals to one tensor D in the tensor product S tensor S over U. Okay, तो आपने जनरल किया ना, A टेंसर B डिफाइन आपने किया है, तो एक्चुअली S जो है ना इट्स यू बाई सिस्टम, दिस S इज आल्सो यू बाई सिस्टम. तो वहाँ पर A और B होते ना, A होता है था वहाँ पर एस टी, देन B वाज टी यू सी, तो बाई सिस्टम्स होते हैं. और तो वहाँ पर अगर आप टेंसर प्रोडक्ट में देखना चाहोगे A टेंसर B और S क्या है, A was this was US system, US by system, and then B was their ST by system. Okay, this is in the middle. और इस केस में एक स्पेशल केस है एक्चुअली. S क्या है, S है UU by system. ओके, और JS भी है UU by system. UU by system दोनों है. The particular case had tensor product है. Okay, it's a particular case. So we'll explain it in the proof also. But first you should at least understand the statement. Statement में जो चीज़ है वो at least clear होनी चाहिए. तो ये if and only if part है, we prove only one part. We prove that if D tensor 1 is equal to 1 tensor D in the tensor product S tensor S over U, then we will show that D is in the domain. Prove. So suppose that D tensor 1 is equal to, suppose that D tensor 1 is equal to 1 tensor D in S tensor S over U, tensor product over U, tensor product of systems over U. S is here UU system, this S is also UU system. So here S is the system and U is monoid. Okay, तो S यहाँ पर सिस्टम, S है मोनाइड भी, बट इट इज ऑल्सो ए सिस्टम. जब आप S टेंसर S की बात करोगे ना, उस केस में इट मीन्स दैट दिस S इज UU बाय सिस्टम. ओके, so suppose this holds D tensor 1 is equal to 1 tensor D. Okay, so we show that D is in dominion. We show that D belongs to dominion of U and S. तो डोमिनियन के लिए क्या लेना आपको, T कोई भी मोनाइड लेना है और कोई भी दो मॉर्फिज्म लेनी है. Let T be any monoid and beta gamma be morphisms from S to T, be monoid morphisms, be monoid morphisms such that U beta is equal to U gamma for all U in U. तो आपको प्रूव करना है D डोमिनियन में है, दैट मीन्स आपको ये प्रूव करना है D बीटा. अगर बीटा और गामा D is dominated by U means that आपको प्रूव करना है D बीटा is equal to D gamma. क्योंकि हम सिस्टम्स में है तो हम सिस्टम के थ्रू ही इसका प्रूव करेंगे. We try to make this monoid T as by system. Okay, we may regard this T as a by system. तो by system के लिए obviously आपको actions define करने हैं. We may regard T as a UU by system. T as a UU by system. Okay, S तो है ही UU by system. Okay, UU by system. We may regard T as a UU by system. If we define the action by, if we define the action by, हम एक्शन को कैसे डिफाइन करें यहाँ पर, तो एक्शन का जो ऑपरेशन है वो मैं डॉट से डिनोट करूँ, U डॉट T, क्योंकि आपको T लेफ्ट साइड राइट साइड में भी लेना है और लेफ्ट साइड में भी लेना है. आपको प्रूव करना T इज राइट U सिस्टम एज वेल एज लेफ्ट U सिस्टम. तो U एक्चुअली U आपको लेफ्ट साइड में पहले लेना है, लेफ्ट U सिस्टम. तो ये एक्शन लेफ्ट एक्शन आप कैसे डिफाइन करोगे, इट्स इक्वल टू U बीटा. ओके, u बीटा किसका एलिमेंट होगा, बीटा इज अ मैप फ्रॉम s to t, u बीटा इज एन एलिमेंट ऑफ t, और t तो t का एलिमेंट है. नाउ ऑन दिस साइड इट्स जस्ट द प्रोडक्ट ऑफ टू एलिमेंट्स ऑफ t, u बीटा इज एन एलिमेंट ऑफ t, t इज एन एलिमेंट ऑफ t. एंड आप ये ब्रैकेट में लिखोगे दिस u बीटा इज सेम एज u गामा. आपको जो यूज करना होगा वो आप यूज कीजिए, ओके, बिकॉज u बीटा इज सेम एज u गामा. इसको आप ऐसे भी लिख सकते हो. एंड लेट्स डिफाइन नाउ राइट यूज सिस्टम, राइट यू एक्शन. ओके, तो राइट यू के लिए आपको क्या करना है, यू राइट साइड लिखना है, टी डॉट यू, और टी का एलिमेंट टी को आपको प्रूव करना है यू राइट यू सिस्टम. ओके, टी यहाँ आपने लेफ्ट यू एक्शन डिफाइन किया, अब आपको राइट यू एक्शन डिफाइन करना है. टी डॉट यू इज इक्वल टू इट्स टी टाइम्स दिस यू, अगेन यू राइट यू बीटा, बट यू बीटा इज सेम एज यू गामा. उसको आप यहाँ लिख सकते, इट्स इक्वल टू टी टाइम्स यू गामा. तो जो डॉट जो नोटेशन है यहाँ पर, ये एक्शन की नोटेशन है. तो राइट हैंड साइड में मैंने कोई भी डॉट वगैरह नहीं लिखा. राइट हैंड साइड में जो ऑपरेशन है वो है सेमी ग्रुप की, मोनोइड की ऑपरेशन, क्योंकि ये सारे एलिमेंट्स टी के हैं. और नाउ यू कैन इजीली वेरीफाई दैट दिस विथ रिस्पेक्ट टू दिस एक्शन योर टी इज यू बाय सिस्टम, यू बाय सिस्टम. दैट यू कैन इजीली वेरीफाई. So let's try to verify it. Okay, वेरिफिकेशन मैं सिर्फ लेफ्ट यू के लिए वेरिफिकेशन करूँगा. सो उसके लिए मुझे दो एलिमेंट्स लेने हैं यू से, मोनाइड से. लेट यू वी बिलोंग्स टू यू एंड टी बिलोंग्स टू टी. देन यू वी डॉट टी इज इक्वल टू, आपको पता है इट शुड बी इक्वल टू यू डॉट वी डॉट टी. यू वी डॉट टी बाय डेफिनेशन इज इक्वल टू यू वी beta t, but beta is a morphism, it's u beta, v beta and t. Now you can apply the associative property, it's equal to u beta then v beta t. This is equal to u beta. Now here you can see v beta t means v dot t. Now this is an element of t because it's an action, it's an element of t, and u beta times element of t is equal to u dot element of t. Element of t is here v dot t. So u v dot t is equal to u dot v dot t, and now let's check that 1 dot t is equal to t, and 1 dot t is equal to, by definition it's equal to 1 beta t, but beta is a monoid morphism, 1 beta is again identity. So identity into t is t. It is t. Okay, so मैं सिर्फ इसको वेरीफाई करूँगा. So check the other, check other properties. Okay, verify other properties. Verify other properties yourself. So this t is u by system. ये आपने चेक किया है. T is u by system. Now let's define a map psi from s cross s to t. वहाँ पर हम कहते थे मैप जैसे टेंसर प्रोडक्ट, वहाँ पर a क्रॉस b टू दैट वो होता था s t बाय सिस्टम. अब यहाँ पर t u बाय सिस्टम है और s का s b u बाय सिस्टम है. अब ये मैप हम डिफाइन करेंगे, हम प्रूव करेंगे ये जो मैप होगी, एक तो ये u मैप होगी एंड सेकंड इट्स आल्सो ए बाय मैप. तो अगर ये बाय मैप भी होगी, यू मैप भी होगी, फिर जो एस और एस का जो टेंसर प्रोडक्ट होगा वहाँ से इस टी तक कोई जो है प्रॉपर्टी टेंसर प्रोडक्ट, इस टी तक कोई मैप एग्जिस्ट होगी जो उस डायग्राम को कम्यूट करे जो कि टेंसर प्रोडक्ट में है. ओके, सो लेट्स डिफाइन दिस मैप. डिफाइन दिस बाय, इसको हम ऐसे डिफाइन करेंगे. डिफाइन दिस बाय एस एस प्राइम साई इज इक्वल टू बीटा, इट्स इक्वल टू एस बीटा and s prime gamma for all s prime belongs to s cross s. So first we check uu is a bimap. This psi is a bimap. Psi is uu map, not a bimap. Uu map check करेंगे. Left u and right u map. Okay. So let's take an element u belongs to u. And an element s prime belongs to the domain s cross s. We have u times s prime and then psi. So this it's a left action here. You have to apply that left. It's equal to u s prime psi. Definition of left action on the action on cross product जो हमने already define किया है. Now let's apply the definition. This is equal to u s beta and s prime gamma. That's the definition of psi, and this is equal to u beta s beta, and this is equal to u beta s beta. Okay, it's u times, okay, whether it's the trivial okay, u beta s beta and s dash gamma, s dash gamma. Okay, so this s beta s gamma, s prime gamma is equal to s prime psi, but it should only u, it should be only u here, it should be only u here, it should be only u here. How do we do that? This psi is a UU map, so it's very important. This psi should be UU map. U लेफ्ट साइड से भी बाहर आना चाहिए और राइट साइड से भी u को बाहर आना है. So it's here u s prime, by definition of action. It is the definition of action. Okay, it's fine. This is the definition of action. Okay, then I have applied the definition of psi here. It's beta of the first element, then gamma of the second element. Now oh yeah, this beta, what is this beta? Okay, beta is morphism. Okay, it's fine. Beta is morphism from S to T. Okay. Oh. Am I right here? It's a product here. Okay, so here is the property of action. It's USS prime, then beta US, beta US. Okay, beta US, it's equal to u beta s beta, and u beta u के बराबर तो नहीं आ जाएगा. मुझे यहाँ पर सिर्फ u चाहिए. I want u here only. So how do we do that? Says it's a UU map. Okay, it's a UU map. Then it's a UU map. Size a UU map. Size a UU map. So what's the definition of action? Let's write definition of action on S cross S. Am I right? What's the definition of the action on cross product? That's in the tensor product actually here. Definition of action on A cross B. Is it in the same way? Okay, let's see that first. So yes, it's right. It's S of xy is equal to sxy. That's right. That's right. So this is right. Okay, it's S US then S cross. Okay, US and S prime psi. Now apply the definition of psi here. That's the beta of first element and then gamma of the second element. This beta is not the bimap. Beta is a morphism. Beta is a morphism. Okay, beta is not a bimap. Okay, psi. So मुझे actually चाहिए this should be equal to s times s beta s prime gamma, that's s prime psi. Okay, u times this मुझे चाहिए, this should be equal to u times this. और इसी तरह से मुझे u यहाँ से भी बाहर आना चाहिए. u I think I am missing something here. I'm not doing the proper steps actually here. That's why this problem is created here. So yeah, it is. So let's leave it this time. So we'll check it in the next lecture. Okay, we'll verify this in the next lecture. And this one, s prime u of psi is equal to s prime psi then u. Okay, this. So this this psi is u map. So we'll see it in the next lecture. This we'll verify this in the next lecture. Okay. And finally, we'll see that psi is a bimap. Okay, it's a bimap. It's a bimap. तो बायमैप के लिए आपको वही आपको u का एलिमेंट लेना है, बिकॉज सिस्टम इज ओवर u, और s प्राइम s क्रॉस s मिलना है. सो लेट u वी हैव दिस. अब एक्चुअली u के एलिमेंट को हमें मूव करना है. ओके, सो ये u का एलिमेंट इस s प्राइम के साथ आना चाहिए. दिस इज बाय डेफिनेशन इट इज इक्वल टू s u beta s prime gamma, and that's equal to s beta u beta s prime gamma. But let's look this. U beta is equal to u gamma because beta and gamma agree on u. It's equal to u gamma and s prime gamma. And now you can see this is equal to s beta, and this one is equal to u s prime of gamma. Okay. And by definition of psi, it's equal to s u s prime psi. So psi is a bimap. This is very simple. Psi is a bimap. तो आपको bimap मिल रहा है s क्रॉस s से लेकर t तक. Now by definition of the tensor product, so there should exist. So therefore, by definition of S tensor over SU, there you can see its definition tensor product. There exists psi tilde from S tensor S over U to T. It's defined by ये जो मैप है इसकी डेफिनेशन ऐसी है, वो आप उसके प्रूफ में देख सकते हो. जहाँ पर हमने टेंसर प्रोडक्ट किया है, इसकी डेफिनेशन क्या है? S टेंसर S प्राइम ऑफ psi tilde is equal to S prime of psi, but this thing is equal to this thing. It is equal to S beta S prime psi. Okay, so this is the definition. Now we had to show that D is in. Now it's given क्या है आपके पास? It's given that D tensor 1 is equal to 1 tensor D. ये given आपके पास है. So आपको प्रूव करना है D dominant में. That means you have to show that D is dominated by U. So we have D beta equal to D gamma के बराबर होना चाहिए. So that's what do we mean by the element dominated by U. Okay. So D beta. Let's find D beta. D beta is equal to D beta into 1 gamma, because gamma is a monoid morphism, 1 gamma is identity T. But by definition, this is equal to D. You can see S beta S prime beta is equal to S tensor S prime psi tilde. So this is equal to D tensor 1 of psi tilde. But D tensor 1 is same as 1 tensor D. 1 tensor D, okay, of psi tilde. 1 tensor D of psi tilde. Okay. So next, now you apply the definition. Now you have here 1 tensor D, that's equal to 1 beta and D. Okay, यहाँ पर मैंने इसको गलत लिखा. It's not psi here. It's gamma here. Okay, it's gamma. The definition is it's gamma. Okay, 1 gamma. So now 1 tensor D of psi tilde. This is equal to 1 beta. This is equal to 1 beta and D gamma, but 1 beta is again identity. This is equal to D gamma. So thus D beta is equal to D gamma, and therefore D belongs to dominion of U as required, as required. And conversely assume that assume that this D is in dominion. We show that D tensor 1 is equal to 1 tensor D. We show that D tensor 1 is equal to 1 tensor